Okay, so let's go ahead and get started. Hello, everyone, and greetings to all our customers joining from around the world. I'm Lokesh Charara, the Senior Manager for Arista's Technical Services team, and it's a pleasure to welcome you all to our exciting webinar series hosted by Arista TAC team. Whether you are joining us for the first time or returning after a break, I'd like to briefly outline the purpose of these sessions. Our goal is to share the knowledge that we have developed in the TAC world with our customers, focusing on the topics that are highly relevant and beneficial to everyone. We launched this initiative in 2022, and over the past 2 years, we have delved into various technical topics. These topics include switch health checks, Layer 2, Layer 3, VXLAN, and EVPN debugging, both from the CLI and Cloud Vision perspective. And recording to all our previous sessions, including the presentation material and Q&As, are available on our Arista community page if you'd like to review them. Starting this year, we are bringing more Arista products into the mix and doing a deep dive into how these products together can offer a helpful platform for debugging any common networking problem. So this is our third session this year, and we also have our Q2 schedule out for the series as well. Coming to today's session, we are going to do a deep dive into debugging packet drops that can occur in any network, and we are going to cover some use cases that we see in our TAC interactions and common problems that we actually come across. We'll go over the debugging steps that can be applied to troubleshoot these problems and EOS CLI tools that will come handy in such situation. So for today's session, we have our subject matter expert, Madhukar Sharma, who will be walking us through these debug scenarios. Madhukar will take us through some lab scenarios that we have encountered in our TAC interaction. And for everyone's reference, we have prepared a lab topology diagram, and we already sent it out to our registered customers earlier last week. Madhukar will be highlighting this topology in between the debug scenarios, but it'll be a good idea for all our customers to take a snapshot of this topology and keep it up on your screen for reference. We have a PDF download link that is our panelists are putting in the Q&A section, so I request everyone to download it and keep it handy during the presentation. Along with Madhukar, we have technical leads as part of the panel who can help answer any question that you may have during the course of this presentation. So you can use our Q&A manager to ask panelists any questions. One small addition before we dive into the troubleshooting scenarios, I would like to highlight our new product offering, which is TAC Custom Training. A little bit about this new product. Based on the valuable feedback that we have been receiving from a lot of you and just a wider interest in overall personalized trainings, we have kickstarted this effort, which is essentially a fully customized training session led by our tech experts. We customize the content of these sessions based on the feature set, platform, and the design that you have in your network environment. We also include our comprehensive analysis of the recent TAC cases as part of these sessions to provide you with a complete view of your network and the problems that you've been experiencing in your network. They also come along with the key recommendation from our experts to overcome these problems to avoid outages. These sessions are delivered in the form of debugging sessions. So they ensure the readiness of your network operations team to handle any such challenges. And since we have started this offering, we have delivered many such sessions to our cloud titans and enterprise customers, and we continue to receive great feedback on quality as well as on content. This is a paid offering, so if you're interested in scoping a session with us or just interested in learning more about this offering, please do reach out to us at tac-custom-training@arista.com. And now, without taking any further time, I'll hand it off to Madhukar for taking you through the presentation. Madhukar, take it away.
Thank you, Lokesh. Good morning, everyone. My name is Madhukar Sharma, and I'm one of the technical solutions engineer here at Arista Networks. Today, I'll be your technical presenter in this webinar on the topic debugging packet drops in a network And in today's session, we will be discussing the useful strategies to debug small scale and large scale topologies in an efficient manner by leveraging the EOS CLI and Cloud Vision, which makes the life of a network operator much easier. Now, before we deep dive into the troubleshooting part, let's take a quick look into the topology diagram that we'll be making use of today. Now, in today's topology diagram, we'll be making use of a spine leaf topology, where we have three set of leaf switches. The leaf 1A and leaf 1B, which are in MLAG, have server 1, which is in VLAN 20, having an IP address of 20.0.0.1 and a MAC address ending in with C361 behind the port channel 20. Then we have the server 4 in VLAN 10, having an IP address of 10.0.0.1, having a MAC address of F6F2 behind the port channel 30. Then we have the leaf 2 switch, which has these connections towards the server 2, which is in VLAN 20 and has the IP address of 20.0.0.2 and has a MAC address ending in with 4A89. And lastly, we have the leaf 3 switch, which has connections towards the server 3, which is in VLAN 10 and has an IP address of 10.0.0.2 and has a MAC address ending in with F820. Now, just a heads up, all these DC leaf switches that you see in the topology are only layer 2 switches. And the spine in this case will be acting as the layer 3 gateway for all of them. We're also streaming all these Arista switches in the topology to Cloud Vision. And the CVP instance that we'll be using for today's troubleshooting is running the the CVP code version 2023.1.0. And just a disclaimer, there's no VXLAN involved in this particular setup. So all the end-to-end communication is happening by the basic IP plane routing model. Now, this topology diagram must have been shared with you previously, but if you guys don't have it, I would request you guys to download the topology diagram and the other partial files from the chat. Our team will be sharing on that. Keep it handy so that you guys can reference it out while we are troubleshooting the scenario further. You would also like to test this out in your lab topology, or you may want to know what are the platform devices we are using. So we've referenced out all the platform models for the respective devices with the EOS code versions they are running. And with that, let's look at the problem statement that the customer informed us. Now, the customer reported intermittent network instability in the setup, where they are observing file transfer between the server 1 and the server 2 to get stalled. Customer is trying to download a backup file, which is present on the server 2 onto server 1, but they are seeing that that process is failing intermittently. Upon gathering more information on this particular issue, we saw that apart from the file download stalling, we also saw the IP communication between the multiple end hosts getting impacted intermittently as well. For our troubleshooting, we are going to make use of a partial topology, as you can see on the screen. And when we asked the customer when did they start to see this issue to happen, they said that the issue started somewhere around March of 11th. Getting to know about one of those past occurrence, we saw that the past occurrence of one of these instances was between 7:20 p.m. Pacific time to 8:30 p.m. Pacific time on the 11th of March. Now, to verify the problem and gain some insights into the frequency of it, let's run a few tests on the CLI of the server 1. And for that, let's go on to the CLI session. For this particular troubleshooting session, I'm going to make use of a pre-recorded video, so please follow along. And I would request you guys to have the topology diagrams handy, just in case you want to reference it out. Now, the first test that we're going to run is the ping test, wherein we are going to initiate an ICMP echo request from the server 1 towards the server 2. And as we can see here, the stream of ICMP responses are coming through and the stream of communication seems to be working as per normal. Well, we don't see any packet loss in any of the responses that came in. And looking at the round trip time of the stream of communication, we can see that it is very consistent without any major deviations. So all in all, the IP communication seems to be working fine between the two servers. Finally, we are going to do a file transfer using the SCP command. And in this case, we are going to download the backup_server2 file, which is present on the server2's temp folder. And we're going to download that or file transfer that file onto the local directory of the server 1. Now, upon getting authenticated, we can see here that, the download of the backup underscore server 2 file has started. And we can see that the download percentage is increasing and the download speed seems to be pretty consistent. Looking at the download time, we can see that, the time is gradually decreasing. So our download process or the file transfer process is proceeding correctly. Now, in a traditional way of troubleshooting a network problem, we are only dependent on our CLI to trace down the path taken by the packet. And for a bridging flow like this, we usually make use of the MAC address table to see where the respective MAC addresses are located and further look at the LLDP output to get some visibility on the connected device. But in this case, we're going to leverage the capabilities of Cloud Vision to look at the full topology widget, which is one of our existing feature and has been discussed in one of the previous webinars. But for the audience who's joining us new today or who hasn't watched our previous content, I would definitely recommend you guys to search for Arista TAC webinar on the YouTube homepage and look out all the previous content that we have created for you. You can also find that on the Arista Community Central page by searching the Arista TAC webinar on the search tab. But coming back to the topology widget gives you a graphical representation of the device connections and also tracks the respective flows from one device to another. Now, some of the things that we can do here is, if we go through these topology and if we see the left pane that's there on the screen, we can click on the flows button and it shows us, all the set of traffic flows which are going through this particular network topology. These flows are sampled onto Cloud Vision via the Arista telemetry agent. And, the topology widget makes use of these flows to show us a graphical representation of the path taken by the respective flows. Now, if we click on one of these particular flows, we can see how graphically, the traffic is traversing through the server 2 towards the server 1. And, we can see what are the respective network devices that the packet is traversing to reach the destination. From leaf 2 to spine and then all the way to leaf 1 and all then reaching the destination server 1, we can see that the packet is reaching to the end destination. And if we look at what are the interfaces that it's ingressing and egressing out, on the leaf 2, the packet enters at ET5 and exits out of the ET51/1 to reach the spine device where it enters on the device using ET50/1 and exits out of ET55/1 towards the leaf 1A, which is the next device. On the leaf 1A, the packet enters on port channel 10 and exits out of ED5 on the Ethernet 5 interface. So this way, we are able to reduce the time taken to figure out the path taken by the traffic flow in the network and are also able to map out the ingress and egress interfaces. Now, upon going back to the download screen, we can see that the file transfer from the server 2 to server 1 has successfully completed. So in this case, we didn't hit the issue that was reported by the customer, that the file transfer didn't hang this time. Now, if we recall, we ran the ping test and then the file transfer test, and both of them were successful this time. So this definitely seems like something intermittent because in this instance of those two tests, we didn't hit the issue. But for now, let's get back to our Cloud Vision screen to look at some data points and get some visibility on what's happening on the devices in the topology during the time of the issue. For that, we're going to go on to one of the devices in the path. So for instance, let's click on leaf 2. Upon clicking on leaf 2, we can see and look for the active events which are happening on this particular device. And upon clicking on the active events, I can see that there are no active events which are being generated on the leaf 2 at the moment. But if I want to look at the previous events that took place, I'm going to go and hover onto the events button that's there on the left. And once I click on that, it loads all the previous events which took place recently. For our troubleshooting, we are much more interested in the timeline which was reported by the customer, which was on the March 11th between 7:20 p.m. to 8:30 Pacific time. So, adjusting our timeline, we can see here that we are observing some streaming latency outside of expected range events that took place on the leaf 2 switch. Scrolling through the other set of devices or the other set of events, we can see that there are only the streaming latency outside of expected range which was reported on the leaf 2. Now, this may or may not be impacting the data plane traffic, but for our troubleshooting, let's go back to the topology widget and look at the other events on the respective devices. So next device in the topology or in the path, which is the spine, we click on the active events to see that there are no active events being generated on the spine as well. And now to look at the past events on the spine device, we're going to click on the the events tab, and we can see here that the timeline is already adjusted according to the issue timeline, which was reported by the customer. Now scrolling through the set of events on this particular device, I can see that there are quite a lot of spanning tree interface state changes that are happening on this particular device. And for reference, let's click on one of them to see what is happening. Now scrolling through these set of logs, I can definitely see that it is the ET53/1 interface, which is going through a lot of spanning tree interface state changes, and eventually it gets into a stable state around 8:27 p.m. Pacific time on the 11th of March. Now this timeline that's there on the logging or the events timeline, we can see that this is coinciding with our issue timeline, which was reported by the customer. So there's definitely something which is causing these spanning tree instabilities during the time of the issue. To troubleshoot this further and now looking at the other events that took place on the rest of the devices in the path, let's go back onto the topology diagram and see the next set of devices. The next set of devices in this particular flow will be the leaf 1A or the leaf 1B. Now, since leaf 1A and 1B are in MLAG, the traffic during the issue state could have hashed to either one of them. In our recent instance, we saw that the traffic was hashing towards the leaf 1A. But just to cover all the devices, let's also look at what were the events that took place on the leaf 1B switch. So once we click on the leaf 1B switch, we click on the events tab and see what are the events that took place during the time of the issue. And we can see here that we see quite a lot of output discards, which reports some packet drops which were happening on this particular device. The queue size above threshold, which was reporting some congestion, some spanning tree events, and a port channel member flap event as well. Let's click on one of these packet drop events that took place on this particular device. And we can see here that this event took place at 7:59 p.m. on the 11th of March. Now, this event definitely coincides with our issue timeline. And we can see here that for a brief period of time, we were observing these packet drops to happen on the port channel 10 on leaf 1B. Going through the other events, such as the port channel member flap events, I can see that the port channel 10 went down for a bit, and after a few seconds, it just came back up again. If I look at the timeline for this particular event, I can see that this event took place around 4:49 p.m. on the 11th of March. Now, although this event does not align with our issue timeline, which was reported by the customer, but there's definitely something happening in the background which was causing these network instabilities, which was observed by the customer. Now to look at further, and let's go back to the topology widget and see what were the events that were taking place on the leaf 1A switch as well. So for doing that, we're going to click on leaf 1A and go to the events tab for the respective device. Now scrolling through these set of events, I can see a lot of these port channel member flap events that took place on the leaf 1A. So now I'm going to click on one of them, and I see some specific information for this event, which took place around 8:22 p.m. on the 11th of March, which is again coinciding with my issue timeline. I see here that the local interface ED56/1 left the port channel for a reason due to partner not collecting, and that caused the port channel to went down. Now, this is one specific information or the specific, topology or specific interface, which was observing some issues, and that caused the, the port channel to go down. So we have one reference point that we can further look into. So when going back to the topology diagram, I would like to show you some cool features that you can even do with being on the topology widget and get some high-level view of the interface. So if you hover onto the interface or the link connecting the two devices, in this case, the link between the leaf 1A and the spine, you can see there on the left pane, you get some high-level visibility on the traffic throughput, the bandwidth utilization, the discard rate, the error rate, and the operating speed between the link between the two devices. In this case, we are much more interested on the leaf 1A's ET56/1. So let's click on that particular link and see what were the interface stats on a granular level. Now, the stats that we want to look are during the issue timeline. So we're going to adjust our timeline view, which is there at the bottom of the screen. And we're going to adjust it according to the timeline which was reported by the customer to see what was happening on this particular link. After setting the timeline, we hit the apply button. And let's first check if there was any congestion being reported on this particular link. Now, LAN-Z is reporting some congestion. Now, for our audience who are not too familiar with LAN-Z or Arista Latency Analyzer is a technology that tracks and logs buffer congestion in latency in real time. The visibility provided by LAN-Z of network hotspots and microburst over subscription gives the network operator a greater insight into when the problems are occurring and why. So in this particular setup, we can see that there is a LAN-Z reporting some congestion on this particular link. And if we click on the graph to get some granular view, we can see that there was no congestion reported during the time of when the issue's timeline started. But scrolling through the graph, we can see around 7:29 p.m. And that's where we started to see the congestion being reported, but only for a few minutes. Proceeding with the graph, we can see that there was no further congestion reported until 7:55 p.m. when we started to see frequent congestion being reported on this particular link, but in an intermittent fashion. Now, these congestions have been happening all the way, and if we scroll through the end of this timeline, we can see that this time, congestion was being reported from 7:55 till 8:20 p.m., which kind of covers the issue timeline as well, which was reported by the customer. So this is one data point that we can see that there was congestion being reported during the time of the issue as well. To further look at other interface stats, I'm going to move on to the rates and counters tab, and I'm going to look at the TX traffic rate first during the time of the issue. So to do that, I'm going to click on the bit rate out, and I'm going to see what were the traffic rates before and after or during the timeline of the issue. So just before the issue had started, I can see that we were sending a consistent traffic on this particular link. From the levels, I can see that I'm sending somewhere around 4.8 gigs of traffic. But if we scroll through the graph, I can see there is a slight dip or a minor timeline where I see a major traffic dip in the network. And this happened around 7:30, but this happened only for a few minutes. After that, we saw the traffic rate to resume back to its normal value. But just after 7:55, I can see a major dip in the traffic again happening more frequently, yet in an intermittent fashion. So this is something to be noted that we are observing this dip in the traffic rates and congestion being reported, and looking at the other details on what I'm observing on this particular link, I can see that there are some pause frames which are received on this particular link. Now for our audience, pause frames are a part of the Ethernet flow control mechanism, which is generally introduced to have a lossless transmission by regulating the traffic levels at the time of the congestion. For example, in a file transfer process, a situation may arise where a sending device may transmit data faster than the destination device can accept it. And the destination device sends a pause frame back to the source device, asking it to stop the sender's transmission for a period of time. And this period of time is mentioned in the pause frames which are being received. This process would happen at every hop in the network between the source and its destination. And for now, let's look at what were the timelines where I was receiving these pause frames on this particular link. Now, scrolling through this particular graph, I can see that there were no pause frames being received until the issue timeline started, but somewhere around 7:29 p.m. is when I started to see some pause frames coming in, but only for a brief period of time. It was only until 7:31, we received the pause frames, and from 7:31 all the way till 7:55, we stopped receiving any pause frames. But from 7:55 onwards, we started to receive more pause frames and being received more frequently, but again in an intermittent manner. So, this gives us some information, and given that we are receiving pause frames in our network, looks like we might have an endpoint that might be getting overwhelmed or has a faulty NIC that is continuously sending us a pause frames. And since we do have flow controlled enable on this particular link, since we have, this would definitely explain why the dip in the traffic since the dip in the traffic, since each time a leaf 1A will receive these pause frames on ET56/1, it will cause or pause the sending of traffic to the uplink in the duration of the pause frame to be stopped. And this would also explain why we were seeing the control plane instability with the STP and LACP, because the normal flow control is agnostic to the traffic class and will cause us to pause all the traffic outbound in the periods of heavy pause frames. Now, this could cause the remote side to time out these control protocols, causing the flaps we are observing, and this could affect all the control plane traffic. But in this case, we are only interested in the LACP and STP events. Now, additionally, while we are going to pause sending traffic on the uplink, that is the ET56/1, if the leaf 1A continues to receive traffic from the downstream, we will have to buffer the traffic till the ET56/1 is free to resume traffic forwarding. And this can cause a queue buildup to happen in the background. And after the headroom of the input buffer is exceeded, we start to see pause frames being sent out to manage that congestion. And if the traffic continues to come in, packet drops are bound to happen when the input buffer continues to remain overrun, which is what we are seeing here with these congestion events, as well as the pause frames being received whenever there is a packet drop, or there is a a spike in the pause frames being received. Now, these are those troubleshooting steps that we took on the CloudVision part. But let's take a look at what are the key takeaways that we can take note from the CloudVision side of things. So as a test, we ran a file transfer of the backup_server2 file by the SCP. And that way, we using CloudVision, we were able to trace the end-to-end path taken by that particular flow. We also saw the network events that took place during the issue state. And some of the notable events that we can see on CloudVision were the packet drops on the leaf switches, the spanning tree interface state changes, and the port channel member flap events being observed on the leaf and some other switches as well. Now, LANZ reported some congestion on that particular link between the leaf 1A and the spine. And the subsequent pause frames being received and the dip in the traffic rate was something that we were able to correlate. Now, at this point from CloudVision, we have a good idea of what might be happening here. And as a next steps, we want to first validate our theory that the pause frames are indeed causing all these symptoms, what we are observing. And for this, let's go back to the CLI and run the same file transfer test that we ran earlier and see if the pause frames are incrementing at the time of the issue or not. But before doing that, let's take a look at how the LANZ events can be looked at from a CLI perspective. And for doing that, we're going to run the show queue monitor length output. Now, LANZ makes use of these three set of flags, which is the start, the update, and the end flag, which specifies the respective events, such as the start flag marks the start of a congestion event on a specific interface. We look at the update flag. The update flag gives us all the subsequent congestion events that took place after this initiation of this congestion event on that link. And the end flag marks the end of a congestion event on the respective interface. Now, some of the things that we can look at on the entry which has the end flag is the congestion duration for that respective event, and what interface were we observing that congestion, along with the traffic class for the traffic being received on that interface. Now, LANZ, just to give a disclaimer, is not enabled on our EOS devices by default. We need to enable it by configuring the queue monitor length in the global config mode. And even if we want to stream that LANZ data onto CloudVision, we need to enable queue monitor streaming on our EOS devices. Now, I know these are some details that you would like to reference out earlier or after the webinar as well. And we're going to provide all these references in the reference slide in the slide deck that we'll be sharing it with you after the webinar. But for now, let's go back to our file transfer test and confirm the additional information, or just to confirm our theory about the pause frames. To do that, we're going to again run the file transfer test. And in this case, we're going to again transfer the backup_server2 file, which is present on the temp folder of the server2, onto server1's local directory. Now, upon initiating the SCP command, I can see it is asking again for a password. And upon getting authenticated, I can see that the download process has started. Now on our leaf switches this time, what we're going to do is we're going to run the multiple show commands, such as the show interface counter discards and the show flow control output to see if there were any increase in the pause frames. But to run them simultaneously, I'm going to run them in conjunction of the run keyword. And to look the details on real time, we can make use of the watch one or the watch one diff keyword at the beginning of the command to see if there are any changes in real time on that particular output. Now running these two commands on both these devices, I can see that there are some output discards which were observed on the leaf 1B's ET51/1 and the port channel 10. And looking at the pause frames output, we can see that there were some pause frames being received on the ET51/1 of the leaf 1B. Similarly, if I look at the outputs on the leaf 1A side, I can see that there were some in discards or packet drops, being observed on the ET6 and the port channel 30 of the leaf 1A. And we can see that the flow control was reporting that there was some pause frames being received on the 56/1 interface, as well as some pause frames being sent out of the device on the ET6. Now with that, we can see that the download process is proceeding and there is no issues, but wait a second. Did we hit the issue again? Now, while we are in the hang state, we can see here that, the in discards are incrementing aggressively, as well as the RX pause frames and the TX pause frames on the leaf 1A side. If we compare the same entry on the leaf 1B side, we can see that the port channel 10 and ET51/1 has no output discards incrementing, as well as the RX pause frames on the ET51/1 is, consistent and not increasing as well. And if we go back to the download process, we can see that while the download process has resumed back, this gives us this test definitely gave us some visibility and some confirmation on what was happening in the background. So we definitely confirmed that it was during when the file transfer was in a hang state that we were observing some pause frames to increment, and that in turn was also causing the input discards to increase, because since we were receiving the data continuously on the leaf 1A, that was causing the input buffer to get overwhelmed, and we saw the packet drops to happen despite the pause frames being received and the TX pause frames being sent from that device as well. Now, although from the topology diagram, we know that the links ET51/1 on the leaf 1B and the ET56/1 on the leaf 1A are connected towards the spine. But just to confirm those things, we're going to run the show LLDP output. And upon running the show LLDP output, I can see that the ET51/1 on the leaf 1B is connected towards the spine device. And the ET56/1 on the leaf 1A is again connected towards the spine device. So that gives us, some information on what is happening and where are we getting these pause frames from. So let's move on to the spine CLI screen to see, is that the device which is originating these pause frames? So to check that, we're going to run the show flow control output again on this particular device. And once we run the show flow control output, and we're going to look at only the non-zero values, we can see here that the ET49/1 and ET55/1 are the two interfaces which are sending out pause frames, but it's the ET53/1 which has been receiving pause frames on this device. So does that mean that the ET53/1 is congested? We can check that using the show queue monitor length output. And once we run the command, we can see here that the ET53/1 was definitely reporting some sort of congestion in the past, but not in the current scenario. Now we would like to see what is this interface connected to. And for that, we'll check on this spine device again to look at the show LLDP output neighbor. And upon running the show LLDP output neighbor, we can see that the ET55/1 is going towards the leaf 1A, which had some increment in the TX pause frames. So that means that is the link which was sending the pause frame towards the leaf 1A. And similarly, the ET49/1, which is connected towards the leaf 1B, was again sending out some pause frames out towards the leaf switch. But the ET53/1 is where we were receiving these pause frames, and those are coming in from the leaf 3 switch. So it's not the spine device which is originating this pause frames, but it was actually the leaf 3 which was sending us these pause frames. Now to track the flow and the next hop, we'll go towards the leaf 3 and see if that device was originating that pause frames or not. To do that, we're going to go into this leaf 3 CLI session. And just a disclaimer that this SSH session that we'll be seeing on the leaf 3 was recorded on the 21st of March. So all the timelines that you see will be in accordance to the timelines mentioned as per 21st of March. Now to check the first output, we're going to run the show flow control output on the leaf 3. And we can see here that it was the ET53/1 which was sending out some pause frames, but it was actually the ET2 interface wherein we were receiving quite a lot of these pause frames. Now going by the main topology diagram, we know that it was the server 3 which was connected to this particular interface, the ET2 of the leaf 3. And when we asked the server team or the customer on what happened or when was this server introduced, they mentioned that this server was brought back up or brought into the network on the 11th of March, which is 10 days from the timeline which was reported here, which is 21 of March to 11th of March. That's a 10 days difference. And that's when, when the server 3 was introduced into this network, started the whole issue. We included the server team along with the customer's intervention, and they were able to identify it was actually the server 3's NIC which was faulty and was contributing towards this pause frames or flow control storm that was being observed. Now, looking at the flow of these pause frames, you can completely understand how these pause frames which were being originated from server 3 were causing a back pressure on the entire network. And because of this back pressure, we were seeing these network instability, such as the LSEP events, the port channel member flap events, the spanning tree events, and we were seeing these packet drops and other data plane issues as well. But just to summarize it, let's go back to our slide deck and look at the summary slide. So at first, we observed that there was some congestion being reported on the leaf 1A interface that was connecting towards the spine. And because of the subsequent pause frames that were being received on these leaf switches, we saw that a dip in the traffic rate was being observed for both the data plane and control plane traffic from the leaf 1A and the leaf 1B side towards the spine. Now that particular drop or the output traffic which was impacted was causing the control plane and data plane traffic to be impacted. And we traced what were the flow of these pause frames to understand which device was the origin for these pause frames. And by running our another test and tracing down the flow control packets being received, we were able to identify that it was actually the server 3 which was sending us these pause frames, and that was due to its faulty NIC. Now we have these set of commands that we made use of to run or understand what the flow control was showing us, where those were coming from. And you might be wondering, since these flow controls, since they are agnostic to the cost value or the traffic classes, how can we prevent this back pressure to happen? Now we can use the PFC with the PFC watchdog for a forced recovery, even during a PFC storm, wherein PFC watchdog is able to detect abnormal back pressure, and it's able to mark the interface or the PFC during a PFC storm. It is able to mark the queue as in a stuck state, and based on the configuration of the PFC watchdog action, the port is either configured to drop all the bidirectional traffic, or it is moved into the error disabled state. So you can definitely use this as a reference, or use this as a solution to avoid these flow control storms and prevent such form of back pressure or network instabilities in your network. Now with that, I would like to call Lokesh back for the concluding comments and answer all your questions.
Thank you, Madhukar, for providing such a detailed overview of this topic. We can move on to the next few slides. Yeah. We trust that this session was beneficial for all our attendees. Again, the recording of this session will be available on our Arista community page, along with the presentation material, as Madhukar mentioned, and as well as the questions which we covered as part of the webinar. As Madhukar mentioned or highlighted in the previous slide, along with the material of the presentation, several good articles are available on our Arista community, which can be helpful for various other topics. So definitely I recommend each and every one of you to leverage that knowledge base. Our next session in the 2024 series is scheduled for the April 24th at 11 a.m. Eastern or 8 a.m. Pacific. So we highly recommend everyone to attend that as well. Taking a cue from the technical deep dive that we just went through, if you're interested in scoping a custom training session with us or just interested in learning more about the TAC custom training, please do reach out to us on tac-custom-training@arista.com. We are also putting a short feedback form, a link with 3 to 4 questions in the chat at this point. So please take some time to provide the feedback, as we definitely intend to use it for our future sessions. And I'm going to keep the webinar open now to wrap up on the Q&As and answer any questions that you may have. At this point, you can use the Q&A manager to ask our panelists any questions. Okay, if there are no other questions, then we'll wrap it up. Thank you, everyone, for joining us today. Looking forward to seeing you at our next session. Thanks, everyone.